So I'll share my screen. Okay, you should be able to see my screen. And these were the ones that we did last review session. So we're just gonna continue from here, from where we left off. So we covered certain I did we go over this? Hold on. We did number 4 here.
Oh, you wanted me to ask you about 5 and 6 for that, for the inverse matrix?
Yes. So 5 and 6 we did, right? 6
Hmm.
we did together. This is all, and this is what I was trying to explain to you in words yesterday.
Hmm.
That um first we did this little like minor pre-processing step, if we will. We verified that these input vectors were a basis. We have more people coming through. We showed that this was a basis because we showed that the row reduced echelon form was the identity matrix, and so they're linearly independent, and you're in a space of three-dimensional space, so your basis must contain three vectors, and the moment you have three linearly independent vectors in a space of dimension 3, it is automatically a basis. So I have a basis. Now, why is this good? Why is it good to have a basis? Well, you can then represent any vector you want in terms of that base as a linear combination of that base of those basis vectors. So we said V, U, and W were that basis. So I'm going to represent E1 in terms of that basis. I'm going to represent E2 in terms of that basis, and I'm going to represent E3 in terms of that basis. So then if you recognize, uh, this matrix is the same for them all. And all I'm doing is I am multiplying, right, on the left by the inverse. So it should come out that if I left multiply, so, right, so then from right here, alternatively, for part A, so if I'm if what I'm saying is, let's see, um, so 1, 1, 0, let me just see, 1, yeah, 1, 1, sorry, I think my sharing screen just died on me again. Sorry guys, I don't know why the sharing screen option is not. Let me see. Let me just pause the recording real quick. Resume. Everybody can see me, right? See the screen?
Yep.
Okay. So where were we? So I'm gonna rewrite the matrix 1, 0. Let me just copy this. Right? And then what was going on? We had A1, A2, A3, and then we're trying to see if it equals 1, 0, 0, right? And then we we solved for A1, A2, A3 by taking this guy, right? The inverse of this, and then we multiply that by 1, 0, 0. All right, guys, I don't know what's going on with this sharing screen thing. Um, Not sure why this happens. All right, great. Hopefully it stays like this. So we kept on doing this, right? So I'm just gonna call this A. So we did A and then we did B, B1, B2, B3, and then we had a 0, 1, 0, and then we had A, I think C1, C2, C3, and then this was 0, 0, 1. So then, Max, you were saying, well, why can't we just expedite the process, right? Um, and you said something was up with that. It wasn't working.
Yeah, because it gave me everything that was like 1/7. Like every single one besides the middle row was a number over 7. But when I did it, it didn't give me the exact same standard matrix that you had.
So it had all the numbers in the standard matrix. It had all these numbers except they were over 7.
For most part, like the middle row, I remember was 0, maybe 1/7, 0. Like the ones that you, when you scroll up a little bit, it was similar to, I think it's further up a little bit more. Those right there, where it's, you see where it says negative 5/7, 8/7, 1/7. It was similar
Right.
to some like that, yeah.
It was similar to something like that.
Yeah.
Now, I'm thinking you can't because let me just see A1.
I mean, I can plug it into the calculator again just to see.
No, no, no. So what you're asking for, like okay. So when you do the inverse, you're looking for the coefficients. What you get out of this are the coefficients. You're gonna get everything over 7. There's nothing wrong with that. I don't know if that makes any sense.
Uh, kind of.
Like I know what you want. You want something like a little quicker way to get to the answer. But I think I think it's okay. Like the quickest thing to do is just to make this a matrix like the following. Call this A, and then this is your A1, A2, A3, right? B1, B2, B3, and then C1, C2, C3. And then this will equal 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then to figure out what this is, you do A, which is equal to A inverse times this, the identity. So actually, um, the inverse of A is precisely the coefficients. So do you see it?
Yep.
I think my screen froze.
Oh, maybe actually it just shows the original A matrix with the identity.
Pardon me?
It just shows the
Yeah.
matrix A
The-
and the identity.
Right. The matrix A multiplied by another matrix equals the identity,
Mhm.
right? Which is precisely what we're trying to look for. We're trying to look for the column of the A column, right? A1, A2, A3, that
Mhm.
gives us 1, 0, 0. Then we're trying to find the B column that gives us 0, 1, 0, 1, 0, and then the C column, which is, gives me 0, 0, 1. That's the quickest way. Now, it's the inverse matrix just gives you those coefficients. Let me reshare. Sorry about this, guys. I don't know what's up with Zoom. So does that make sense? I don't know if that makes sense, Max.
I mean, it
I
does
don't know if it
in
doesn't
the long
suffice.
sense, yeah.
Huh?
It does make a sense in terms of how it's broken down.
Yeah.
Because it does give me the exact same numbers like 3/7, -5/7, 2/7 for the first row for the B of one, B of two, and B of three.
Right. I'm just thinking maybe there's.
I wonder if I can copy and paste this because I'm using an online calculator. Okay, yeah, here. That's the inverse that I get for that. I posted in chat.
Yeah. And that is precisely, isn't that what we get for all of them? Yeah. Those, that inverse matrix you got are the columns are the coefficients for the respective uh s- um like we do here, right? So A11, that first column represents those coefficients,
Mhm.
and then so second column perfect, and then third column.
So when I multiply this by the outputs for T of whatever the input is, it should give me the standard matrix.
No. You want to, so what you're saying is you're gonna put all of these guys into a matrix and then multiply by A inverse?
Yes.
Yeah, it's not gonna work that way. Yeah, it's not gonna give you the standard matrix. Yeah, I don't, it's not gonna give you that. So you're gonna have to do it in this procedure. We will talk about the change of basis, which may help you in the efficiency part, which we're kind of touching upon a little bit, but we haven't touched upon change of basis at the moment. So, okay. Any other questions about this? So 5 and 6 are the same idea. It's the same thing. If you can do 6, then you can do 5. It's just with two dimensional, right? All right. Boy, oh boy. All right, great. So this will not bug out on me. Thank you. I used to go through different ways to like connect by cable, but I think Zoom has updated, so now it's much better. Good. All right. Great. Let's do it. Where do you guys want to go after this?
Professor, actually, just one quick thing. I did just plug in the math for it, and it gave me the exact same standard matrix. I think I made a mistake before, but we can move on past that.
Okay, great.
So there was just an issue with my math when I originally did it because it
Yeah, I
gave me a
was
new
gonna
matrix.
say when you brought this up yesterday, I'm like, there might be some computational, you know?
I realized it might have been a mistake with the original sheet
Yeah. So
because
then,
I looked at the new one and the old one, and I got two different things.
okay, great. So now you have a expedited procedure. Great. Anyone else?
Professor,
Yes?
I have a question.
Sure.
2.1 and problem 2.
2.1. This one?
Mm-hmm.
Problem 2.
And D.
D.
Yeah, I got a different number,
Oh no.
so just
All
want
right.
to
So
check.
let's check it out.
Mm-hmm.
All right. So we're doing number 2, part D. We have a matrix that's 3 by 3, and the determinant of that matrix A is 4. We have a matrix, another 3 by 3 matrix, um, whose determinant is -7. And let me just copy this down. So first of all, this 10, how is this gonna affect the determinant, or how do we take care of that constant?
10 to the third power?
Right, that's right, 10 to the third. And then we take the determinant of the rest, right? A, B, A, -3, B, -4. And then 10 cubed is 1,000. Okay? And then what do we do next?
Calculate determinant A. And
Okay.
separate?
You could definitely separate them, right? We know we can do this. A times determinant of B times determinant of A to -3 times determinant of B to the -4, right? Sorry, B -4, correct?
Mm,
But then we know that the determinant of the inverse, right, is 1
mm,
over that, right? And this same thing goes for here. Let me just. So we know
mm,
that the determinant of A multiplied by B is equal to the determinant of A times the determinant of B. We know this.
mm,
We also know that the determinant of A inverse is equal to 1 over the determinant of A. Um, we also know that, so from here, then the determinant of A to the K should equal what?
Determinant A to the K.
Yeah. Take the determinant of A and then just raise that to the kth power. Right? That's exactly from this property. Now we're just reiterating over a product of the same matrices. So if that's the case, then we have the determinant of A times the determinant of B, right?
Mm,
So I have this 1,000 here. But then I can rewrite this now. And then I'm going to rearrange this. So this is the determinant of A over the determinant of A cubed times the determinant of B, and do the same thing here, over the determinant of B to the 4th.
mm,
Now, what cancels out? Determinant of A with
mm.
this guy, that becomes a 2, this becomes a 3, and this becomes a 1. So then really what I got is 1,000 divided by the determinant of A squared times the determinant of B cubed. Then I have 1,000. Determinant of A was what?
4.
4. So I got 4 squared. And determinant of B is
-7.
-7 cubed. So then I get what? get 1,016 times what? Negative 729. And let me
Yes.
see, what did I write? So what did I have as the answer? Was it completely different?
Why does negative 7 to the third power is negative 729?
Oh, sorry. It's not, it's 343, right? Sorry.
Mm.
That's right. 343.
Oh,
What do I have as the answer? Two 2.1. I got 125 over 2744. Is that wrong?
then maybe I was wrong.
So I believe the answer is in reduced form. I believe. Let's see, 343. Actually, you're right. Wait, what number did you get?
Because I just wonder, because determinant B is negative 7, right?
Correct.
So if we cancel out in the process, I mean the upper part,
You can cancel an 8, right? So
I
if we
mean
put
we
125.
cancel out the determinant of B in the numerator, right?
We do. Yeah. Yeah, we do, right?
But
Because Mhm.
but does it? I mean, does it change the sign or no?
Determinant of B.
Hmm.
Well, you cancel out with one of the determinants of B's, so
Because determinant B is negative 7, right?
yes.
So I mean,
So if it's a negative
does it
7 powered negative,
affect the sign in our calculation or?
determinant of B being negative 7 is like it cancels out with one of the negative sevens. So it's just positive 1 when you cancel it out,
Oh,
right? And so this negative 7 is
mm,
determinant of B, and I cube it, right? So
yeah.
the answer
Yeah.
should be
I got negative 125 over 686.
that's right.
Yeah, that's my answer.
Right. So you have been awarded 1 point.
Thank you.
You found it. I mean, you find it, you tell me, and I stand corrected, and boom. So yeah, it should have been 125 over 686. Um, yeah. Any questions about part D? Everybody follow that? So I'll make the correction on the answer key. Any other questions?
I have a question.
Sure.
아니, part 3.2 basis.
For 3 points, yeah.
And number 5, find the standard basis vector.
Yes.
I don't know how
I
to serve.
You
oh,
don't know how.
after I did have a question too for number, I think it's 1.2, number 4.
Okay.
When
So
after you finish with this one.
sure. 1.2 number 4, that's the next one. Next in queue. Yeah, and if you have any questions, like if you just want to put them on the chat if you want, like you can also do that. just queue them up, and then we can just go right at it. All right. So you said number 5, you don't know how to start, right?
Mm.
Okay. So they're asking you for a standard basis vector. What are the standard basis vectors in R3? E1,
E1,
E2,
E3.
and E3, right?
Mm.
And then it's saying we have these vectors in R3. And we need an additional vector so that we can create a basis. Now it's saying which one of these would give us a basis. So which ones of these vectors do I include in the set v1 to v2? Like which one should I include? Should I include e1, e2, or e3? One of
Mm.
them seems to be good. That's what the question is assuming, right? That
Mm.
one of these standard basis vectors is would be the just adding it to the set of vectors would make a basis. Now the easiest way to do that is to like put it in a matrix, put the columns in the matrix. So I would just say like -1, 2, 3, and 1, -2, -2,
Mm.
and then try them. Try 1, 0, 0.
Oh.
Now,
Oh.
if it's a basis, then what would be true? If I do RREF, right, I
Yeah.
should get
I
the identity. If I don't get the identity, that means that
is a basis.
there's linear dependence, so there's
Mm.
not a basis. So
Oh.
you can try that. Like you can literally put that in your calculator,
Okay.
right? So
Yeah.
let's see if this one is good enough. So 1, 1, 1, 2, -2, 0, 3, -2, 0. And then if I do the row reduced echelon form, I get the identity. This is good. So,
Okay.
so this is the identity.
Mm.
So if I include E1 to this,
Mm.
it's a basis. It is now a basis for R3. Why? Because it is linearly independent. You're in a three-dimensional space and you
Mm.
have 3 vectors. So you
Yeah.
automatically will span. That's one of the nice things about this. So if
Mm.
you know the dimension of your space and you have that number of dimensional vectors, if you
Mm.
just show that one of the 2 conditions for a basis holds, then you have the other condition automatically.
Mm.
Yeah,
Okay. Thank you.
sure. So that's this problem, and the same thing goes for the part B, same idea. So then Oren, you're saying 1.2 number 4, right?
Correct.
So this one here. It says
Oh,
find the standard matrix for the transformation defined by the equations. So um, let's take a look at this. Just so I want to find the standard matrix. This is a transformation, right? So remember what we proved? We proved that every matrix transformation is a what? Right? They go hand in hand. If you have a linear transformation, then you automatically have a matrix transformation and vice versa. Um, so uh, all this question is really asking you to is to like rewrite this and express it as a matrix system or like a matrix transformation to call it. You can call it a matrix equation. And we've done this. This is also like week 2 or week 3. Um, what do we have here? We have 3 unknowns, x1, x2, x3, and then we have the output w1, w2, w3. Can't we write this as 7, 2, -8, 0, -1, 5, 4, 7, -1. This is my coefficient matrix. Then this is the unknown vector n1, x1, x2, x3. And I get w1, w2, w3. Isn't this it? Right?
And that's it. Because I just wanted to know if like what had to be like the end notation, because
The
when I
standard
was doing it,
yeah.
it just so you just have to just put it in a matrix basically.
Well, you have to understand why. You have to understand why just making it into a matrix is indeed the standard matrix representation. Now, the reason why I kind of suggested this understanding of linear transformation is to see that what are we like, okay, so you can look at it this way. You can look at it as some transformation is taking the vector x1, x2, x3, right? And it's outputting another vector in R3 again. So it's also good to know that T is going from R3 to R3. So this transformation is actually a linear operator as well. You can call it an operator because it's it's mapping something from the domain to the same space. So the domain and the codomain are the same. Um, if you notice, the W1, that's the resulting first component of the image of T. So this is the first component, the second component, and the third component. So I would write it like this: 7x1 plus 2x2 minus 8x3. Then negative x2 plus 5x3. And then 4x1 plus 7x2 minus x3. You see that? Normally you've seen this. But I can also write it as a matrix, as a system of equations. It's the same. And then how do you find the standard matrix representation? What do? TE1, TE2, and TE3. Like this is like the systematic way, right? All the way through. When you plug in E1, what are you plugging in? You're plugging in 1, 0, 0. You're plugging in 0, 0, and you're plugging in 1, 0, 0. That's what you're doing. And what do you get for the first column? 7, 0, 4. You get exactly what we got when we just rearranged it as a matrix equation, though. But I'm doing this way so you know for a fact that what you just did in a short way, right? In a shortened way, is precisely what I'm looking for. And why is it that? Well, I'm showing you. Then the same thing happens, right? When you do we do 0, 1, 0, you do 1, you do 0, you do 0, 1, 0. You're plugging in E2 into my, right? You're plugging E2 into the transformation. And what do you get? You get precisely what you thought you would get, -1, and you get 7. And same thing goes for E3. You get -8, 5, -1. And these are the what? These are the columns of the standard matrix representation. That's how this thing goes, right? Does that make sense?
Well, 100%. I had just wanted to know which, so either form is acceptable, or like, do we have to do it that the more, I guess, like broken
Everyone wants the
down way?
shortcut, right? Everybody likes that shortcut, right to the. Let's cut to the chase, shall we? On the exam, right? If you give me this, and if I give you this, if I give you this question, and you give me this, full credit. I can't not give you that. This is like the more what is it? Like the educational route. It's like everything's, you know, connecting. Everything is going logically, flow. Here is just here's the answer. But you're getting the same. It's the same thing. It's the same. So again, that's if I give you this question, right? Big if. Anything else?
That's it for, well, I wanted a question on a proof too, but I have to pull it up.
Yeah, we can talk. We should be talking about proofs. We should be talking about proofs. Definitely. Up until Orin gets it pulled up. Would anyone else? No other questions. Good time to ask if you have questions. If you have any comments, any thoughts on the matter of what we're looking at, transformations, standard matrix representation, determinants, computing determinants, subspaces, hello. 4.1, 4.1. Okay, 4.1.1.b. Very good one. This is a very good one. Yeah, this is a good one. So, trace. Okay, what is trace again? So we denote trace with TR. What is trace?
The diagonal.
What about the diagonal?
Oh,
What about the diagonal?
add a sum of the
The sum of the diagonals, right? So we're summing. What are we summing up?
I
I goes from 1 to
to
4, right?
mm-hmm.
Okay, the trace is just, so we have some kind of matrix. So let's say A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So we have some matrix A, and we get the trace by looking at the diagonal, right? And adding them up. So the trace of this A matrix would be A plus F plus K plus P, correct?
Mm-hmm.
What are we looking for in this problem? We're looking for the what?
Dimension.
The dimension. Okay. Now, what's the dimension again?
Number of vectors in that basis.
Good. So that's the first definition we came up in this class, right? We said that the dimension of any space, vector space, subspace, is the number of basis vectors. All right. And then I gave you like a second way to consider dimension.
Degrees of freedom.
Right. So dimension is the number of basis vectors, number of basis vectors in in sorry, number of basis vectors um of the space. And then this is like the first way to think about it. The second way to think about it is quote unquote degrees of freedom. So it again, they're the same idea. They're the same thing. Okay. It's just that using degrees of freedom, you have more freedom. If you looked at it from this perspective, you would have to tell me a basis for this space and then tell me, oh, there's how many there are. And I'm not asking you to do that, at least not for this problem. I'm asking you what are the degrees of freedom in a sense. So
Mm.
this space, what is the condition on this space? What's the condition?
Um,
What makes up this space? What are the elements of the space? What is
Mm.
inside of the space? Vector space. No? Well, so we have a space, right? That's what it's saying. We have a vector
Mhm.
space. So we haven't really completely defined all the characteristics and properties of a vector space, but we've been dealing with vector spaces this whole time. It's a
Mm.
space of quote unquote vectors that
Mm.
have certain properties. You add them, you're in the space. You scale or multiply them, you're in the space. Zero is in the space. All these
Mm.
properties, right?
Mm.
What's inside this space?
Mm.
They're 4x4 matrices. Vector spaces can be made up of matrices. We haven't seen that formally yet, but we have seen it little here, bits and pieces in the past review sheet and maybe in some of the homework problems that you had on the web assignment. Matrices themselves can form a vector space. And I've also mentioned in passing that polynomials,
Mm.
functions, can be considered a vector space as well. And you can extend this idea of vector space beyond the vectors that you've seen and so familiar with in Rn. Up until this point, we've been just dealing with Rn, 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 Euclidean space, Euclidean space, Euclidean space. But there's other spaces that are also considered vector spaces. But besides that, okay. So I know this might be a little hard at the moment, but like let's call this vector space W. Now, how do I define W? It's the set of all vectors. So I'm matrices. So I'm gonna call it A, right? And A is in the vector space of 4x4 matrices. And then what's the condition? So you should already start to think about this is what are the elements of W,
Mm.
right? This is called set builder notation. How do you create, how do you, what's the notation for how do you define a set mathematically? Well, we use these curly braces. We write something down and then we draw a line and then we write other things down, right? But there's a
Mm.
reason why we do that. It's not just for the sake of it. The first part of this notation is we're saying what's in W. What's in it? Well, they're all 4x4 matrices. And then after that, we write, this is like saying such that, right? This is like saying
Mm.
such that what? What's the condition to be in W?
Trace equal to 0.
That's right. That's all it is. So all I'm doing is I'm writing this stuff down in a notational, consistent manner, and it shortens writing all this stuff out in words. So all of this that I've written here in words is now rewritten as a set, right? And set builder
Mm.
notation. And I'm just gonna have to specify a trace of A is 0. Okay. Great. That's what W is. We're looking for the dimension of W. This is what we're looking for. Now, W again is a set of all matrices that are 4x4 whose trace equals 0. Now look, we have a general a 4x4 matrix, and we know that the trace is 0. Now let's talk about the degrees of freedom. Now, does this value here affect the trace at all?
No.
So can I choose anything for B?
Mm.
I have freedom to choose.
Yeah.
How about C?
Mm-hmm.
How about D?
Oh.
So then you start realizing, oh, this guy, this guy, this guy, this guy, all the entries in my matrix that are not the diagonal are free. Free to be whatever they are and not affect being in W.
Mm.
Degrees of freedom. So I have what? 1, 2, 3, 4, 5, 6, and I have another 6 on the other side. So I have, so far, I can say I have at least 12 entries that can be whatever they want. Correct?
Mm-hmm.
Okay. So now really what the question is this. How many degrees of freedom do I have here? That's really the question. So what do you think?
3.
How do you know?
Oh.
Because the answer said 15. All right. I have 12. I just need 3 more. But there has to be a reason why. There has to be a very good reason why the degrees of freedom here are precisely 3 and only 3. Any thoughts about this? This is a very important scenario
Mm.
here.
If I set the equation like A equals negative F, negative K, negative P.
Sure, you can say that. A is equal to negative F, negative K, negative P.
Then I have three variables.
Yeah. You have 3 free ones, right?
Mm.
And that's precisely it. Like this is similar to let's see. I can do this. Look, 1 1 1 1 A F K P equals 0. Isn't uh this the same as A plus F plus K plus P?
Oh yeah.
It is, right? So
Mm-hmm.
of course, like we don't see it this way, at least not before this class. Now with this class, I can I can have equations and create a matrix version of it. In this case, the matrix is a vector. It's a row vector. And then the column are the unknowns. And it's equal to 0. What kind of system?
Oh.
Oh. What kind of system do you have?
Homogeneous.
Homogeneous system. This is a homogeneous system. And then what? How do you solve homogeneous systems? We take our matrix and we apply what? Reduce row echelon form and all that, right? We apply
Mm-hmm.
Gaussian elimination, right? But then
Mm-hmm.
guess what? This is already in what?
Yeah.
It's already RREF. I have
Mm.
how many pivot variables? 1.
1,
So then what are the rest going to be?
3.
3. Which means I can do whatever I want.
Oh.
So then if there's 12 free entries and I have 3 free here, out of this guy I have 3 that are free. The moment I select those three free variables, automatically the pivot variable is completely determined.
Mm.
So the dimension of this guy is precisely 15.
Mm.
Now, if I really want to go all the way through this, right, I would, what would I do? Like, I want to know, this is actually a good exercise. I want to know the null space. So what would be the null space? What would that look like? So the null space looks like something, right? It looks like A, F, K, P.
Mm.
That's what the vector is going to be, right? So implicitly, when I write here, I'm saying that this is in the null space of this matrix.
Yeah.
That's what I'm saying, right?
Mm.
Or in this case, a vector, but it's a matrix, right? It's a 1 by 4 matrix.
Mm.
So I'm looking for the null space of this matrix. I want to know what are the things that when I multiply this matrix by gives me 0. What
Mm.
are those things? What do they look like? Well, you kind of already solved it here. You already solved it.
Mm.
A is negative F, negative K, negative P. So I can write it this way. Negative F, negative K, negative P. What's F? It's F. What's K? It's K. What's P? It's P. But then what can I do here?
F,
I can say negative F. F, 0,
F,
0.
0. Mm.
I can say what?
Table K,
Negative K, 0, 1,
1,
K,
0.
0. Plus negative P, 0, 0. That's funny. That's funny. You can take out the F, right? Negative 1, 1, 0, 0. Plus K is what? Negative 1, 0, 1, 0. And then what's P? Negative 1, 0, 0, 1. And this is the null space.
Mm.
This is the null space of what? The null space of 1, 1, 1, the matrix 1, 1, 1, 1.
Mm.
So then what's the basis? There's going to be a question on it. What's the basis of the null space of this matrix 1, 1, 1, 1? The basis is the vector
Mm.
1, negative 1, whoops, negative 1, 1, 0, 0, negative 1, 0, 1, 0, negative 1, 0, 0, 1. This is a very good problem
Oh.
because it looks deceptively easy, and then it's like, oh wait, it's not as simple, and then there's a lot of information you can
Mm.
take from it, you can extract from it, and this step of having a matrix being multiplied by a vector and giving you 0 or the 0
Mm.
vector, this homogeneous system is very important to know how to do. You have to know how to find the null space, and you should know how to find the basis from finding what the null space is. And again, F and K and P are what? F, K, and P are real numbers. And these are the free variables.
Mm.
These are the ones that are free. I can choose whatever I want for these, and I'm still in the null space.
Mm.
So very good question.
Thank you.
Yeah. Okay, so Oren says the algebra proof 2. So, okay. So you're asking me about, so proof of 2. So what's 2? 2 says let V1, V2, Vk be vectors in Rn. Then the span of vectors v1 all the way to vn is a subspace of Rn. That's the one, right, Oren? I'm assuming that's a yes. Okay. So, how do we prove that any set is a subspace? So how do I prove that something's a subspace?
3 conditions.
3 conditions. What are the first one?
0 vector.
0 vectors in it. So first we show that 0 is in the span. So in order to do that, I must know the definition of span. And the definition of span is the set of all linear combinations, right? So then now the question is, can 0, the 0 vector, be written as a linear combination of v1 dot 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 to vn? Sorry, vk. Sorry, we used the word vk. This should be k. Okay. So how would one write c1? So c1 v1 plus ck vk equals 0. How do we express 0 as a linear combination of v1 through vk? Anyway, what would be the coefficients of v1 through vk?
Or zeros?
They're all zeros. So let c1, c2 all the way to ck be all 0. Right?
Yeah.
Then 0 times v1 plus 0 times vk is 0. Hence what? 0's in the span. So I showed that 0's in the span. Why? Because I was able to express 0 as a linear combination of v1 through vk. And obviously, it was very simple to do that. Just make all the coefficients 0. So that's the first step, first phase. Now, what's the second phase? Second phase is we show what? What's the second thing we have to show?
Closed under addition.
Yes. We have to show that span is closed under addition. What does that mean? What does that phrase closed under addition mean? Anyway. What does it mean, guys? Hello?
If I add 2 vectors,
Yes.
then together S is also in the span.
Right. if two vectors are in the span, then when I add those two vectors in the span, I'll get the result still being in the span.
The span.
That's what closed under addition means. So then I would say, well, closed under addition, i.e., in other words, if U and V are in span, actually, let me use different, not V. Let me use W. So if U and W are in the span of V1 to VK, then U plus W will also be in span. Well, a lot of this is just like just application of definition. So I'm applying the definition of what closure and addition means to a particular set. The set here is the span of a set of vectors. So span of a set of vectors is a set. And what's that set? It's the linear combination. It's all linear combinations of the vectors v1 through vk. So we want to show this. So because u and w are in the span, each one of them can be written as a linear combination of v1 through vk. So since u is in it, then so I should say we have that u can be written as a1 v1 plus a2 v2 plus ak vk, right? This is what that means. U is in the span of v1 through vk, so I can write it as a linear combination. And what else can I do? W also can be written as some other linear combination. That's purely by definition of being in the span. Now, what's U plus W? Well, it's A1 V1 plus A2 V2, right? Plus all the way to AK VK. And this vector is being added by B1. V1 plus B2. V2 plus all the way to BK VK. But then what can I do with addition? Addition has many very nice properties, right? It's associative, it's commutative, and it contains the distributive property. So I use those properties to my advantage. I say, well, if it's associative, I can reassociate the sum. I don't have to do this first and then that do this first sum and then do this sum first. I don't have to do it because it's associative. And then on top of that, it's commutative, so I can change the order of addition around. And I'm going to do so in a very special way. I'm going to do so that contains A1 V1 and B1 V1, right? And then I'm going to associate those things together. Then I'm going to do A2 V2 and add it to B2 V2 and associate those. Dot, 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 AK VK plus BK VK. So all I did was I rewrote what I was written on top. Now I reassociated them. And then by the distributive property, what can I say? A1, B1, A1 plus B1 times V1 plus A2 plus B2 times V2 plus dot 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 AK plus BK VK. Now, what did I just show? Hence what? What's the conclusion here?
U plus W are in the span.
because u plus v is written as a linear
Stop here.
combination of v1, v2, and vk. I did it. Hence, u plus w is in the span. That's exactly what I wanted to show. Again, what does it mean to be in the span? It means you're written as a linear combination of the vector. So I did it. That's the second phase. So the first phase is the zero element, right? Is in the span. Then the second phase is that u plus, I should say, closure under addition. Now, what's the third phase?
Closure under scalar
Scalar
multiplication.
multiplication, right? So lastly what? Lastly, if C is an R and do a different letter. Let's do U. If U is in the span, then what? Show. Lastly, I want to show, sorry, let me make this a little cleaner. I want to show if C's and U is in this, then CU is also in the span. So then I use a definition. Using the span means that there exists scalars such that U can be written as a linear combination. Okay? Then what? Then multiply C times U, and what do you get? You get C times all of this. A1 V1 plus A2 V2 plus AK VK. What is this equal to? By distributive property, you get CA1 V1 plus CA2 V2 plus CAK VK. But multiplication is associative. So I can associate this, and associate this together. But what have I just accomplished? CU is a linear combination of V1 through VK. Hence what? Hence, CU is in the span. And this is the third, right? This is called closure under scalar multiplication. So by these three properties, we can conclude, thus, the span of a set of vectors in Rn is a subspace of Rn. Oren, does that make sense? I hope so. Any other questions? Any other proofs? Gotta know your proofs. Four point one two B. Sorry, did you mean 4.12? Like this? 4.12B, this one?
No,
No.
4.1. Yeah, dimensions. Oh,
B. This one?
oh,
Oh,
sure.
oh. We're not gonna do those.
Oh,
Yeah, I eliminated. I had. Did I update it? I updated it. There's an
also,
update to that. The
also
one that you see with like
yeah, polynomial
polynomials,
thing.
we
Mm,
haven't touched that, so don't worry about
uh,
it. Yeah,
okay, thank you.
yeah. It's one less thing to worry about. Oren, you said 3.2 to 2B. I only see here too. This one?
The one under it. And which one do we not have to worry about as well?
So like you know how we have this section here, 4.1 dimension. There on the very first version that I sent out, there was a 1 and then there's a 2. And these had like part A and B and they had like polynomials. I took that out. So that whatever you see now in the whatever you see right now on the CUNY Blackboard, that's what you should worry about. That's the updated one. Not these. So these guys here, you don't have to worry about that. At least not for this exam. And or were you talking about this one, 3.1?
The one under it. Oh, was I looking at the wrong one?
3?
It's 3.2 number. Oh, it says number 2 on this sheet, but it's the one under it.
This one.
No, other side.
This one.
Oh, I guess your sheet is a little different than the one that's on Blackboard.
Yeah.
Uh oh, okay. So I think it's 4.2
Oh,
number 2.
4.2. Number, yeah, it's 4.2. Number which one? This one, 2B?
Yeah, there we go. Yep, 2B. Yep.
Oh, yeah, okay. So I
Or
just
did I miss
happened
that
to,
one?
huh?
Oh, did I miss that one? Or
What do you mean, did you miss that one?
because you have it circled already.
No. The funny thing is, if you look at the chat history, the one right before you, Susong said 4.1.2B, and that's the one I said, oh, this one? And then you write 3.22B, and I'm like, it's this one. But then the one that I selected for her was the one that you wanted. So it was because of that. Okay. So I want to figure out the general solution to the non-homogeneous linear system and then find the general solution to the homogeneous system. Okay. So to do this problem, it's a very standard problem, right? It's the same old thing about just solving, right? So let's solve this thing. How do you solve this? Well, I would put it in a matrix. What does the matrix look like? 1, 1, 2, 1, 0, 3, 2, 1, 3, right? This would be the coefficient matrix. Then I would have a corresponding column vector, x1, x2, x3. And this will equal 5, negative 2, 3. Agreed? We've seen this time and time again. I want to solve it. So then how would I solve this? Okay. think. So the first thing I'm going to check is if this matrix is invertible. So I'm going to put in a matrix in my calculator. And to check really quick, I find the determinant. And so this is good. So because this is good, so this is invertible, right? So A inverse exists. What that means is x1, x2, x3, and this is A, right? It's equal to A inverse times this. And if you solve the system, let me just, so my inverse matrix is -3/2, -1/2, 3/2, 3, 2, -1/2, -1/2, 1/2, 1/2, -1/2, right? I would got 5, -2, 3, left multiply, and I get the answer. I get my solution. What I can also do is you guys know several ways now to solve systems, right? One way is by doing this matrix multiplication by the inverse, and the other way is by augmenting the matrix and row reducing it. And so if I do that instead, 1, 1, 2, 1, 0, 3, 2, 1, 3, and do 5, -2, 3, and row reduce that, I get the identity, and I get -2, 7, 0. So my answer will be -2, 7, 0. And that would be the solution. Um, what would be the homogeneous solution to this particular problem? Well, the thing is, because A is invertible, there's a whole slew of things that's true. Okay. If A is invertible, A inverse exists, right? If A inverse exists, what else is true? Row reduced echelon form of A is what? The identity. If that's true, then what does this mean? There are n pivots. If that's true, then what does that mean? There are 0 free variables. If there's 0 free variables, what does that mean about the null space?
Null space is 0.
The null space is only 0, meaning it only contains 0. Because it's only the trivial solution. So then all of a sudden, all these things work out, right? Has n linearly independent columns. So on and so forth. Like all these things are true. All these things are equivalent. If I have n literally independent columns and n by n matrix, then the null space is 0. Then it has 0 free variables. Then it has n pivots. Then it has row reduced echelon form being identity. Then it's invertible. All these things are the same. So since this is invertible, the null space, x can only be 0 and nothing else. So in this scenario, it's almost, you can say it's not that interesting. It's not that interesting because the non-homogeneous system is a unique solution, and the homogeneous system is also unique. It's only 0. Does that make sense, Oren? But I think what would be more beneficial, let me just see if it might be more beneficial to look at C. Yeah. So let's look at C. C is C may give you more understanding of what's going on. B, what's up with B? B is when things work out. Like what I mean by working out is that I have an invertible matrix. My system isn't, I can find the, oh Lord, is not what I wanted. B is the uninteresting case because things go exactly the way you want it to go, as planned.
Oh,
You want to have
Professor.
one solution. Yes?
So what's the answer for the B? Because I said in the review sheet, I said the same answer as A.
Same answer as A? Oh, does it have the same answer as A? Is that what you're
Oh,
saying?
yeah.
Oh, that's my mistake. It does have the same answer as A. That's my mistake. I have to change that too.
So what's the answer?
Oh, the answer. The
Hmm.
answer, the non-homogeneous general solution
Yeah.
is this.
Mm.
And the homogeneous solution is this.
Oh,
It's not that interesting because the general solution is just one solution.
oh, yeah.
And same thing goes for this guy. It's just one. It's unique. And the only reason, the only way, the only time that a system, a non-homogeneous system, has only one solution, and the homogeneous system has only one, the trivial solution, is if A is invertible.
Yeah.
If A is not invertible, then there's more to say. You're gonna have free variables. With the free variables, you're gonna have more, you're gonna have infinitely many solutions for the homogeneous system, which would mean I'll have infinitely many solutions for the non-homogeneous system. Okay,
Mm-hmm.
so let's look at C and see what goes wrong here in this case. So I'll do the same thing. I'll do 1, -2, 1, 2, 2, -4, 2, 4, -1, 2, -1, -2, 3, -6, 3, 6. This is the coefficient matrix. Then what do I have here? X1, X2, X3, X4. And this will equal what? -1, -2, 1, -3. Now, again, there's several ways to solve this, right? One way is to do the determinant. But when you find the determinant of this guy, it's 0. If the determinant is 0, what do we know? A is not invertible. But what does that have to do with my system? Does it mean it has no solution? Not quite. So the determinant being non-zero, being 0 does not mean there's no solution. There may or may not be. But for sure there isn't just one unique solution. When the determinant when the matrix is invertible, the determinant being non-zero, you're going to have only one unique solution every time. But here you may have infinitely many, or you may have none at all. So then what's the way we carry out our solving now? Well, the only way that works out no matter what is augmenting the matrix and performing Gauss-Jordan elimination, which is your calculator does. So I would put this matrix in my calculator. This will be a 4 by 5 matrix, and I'll put 1, negative. Okay, those are already there. So this is -1, -2, 1, 3. Look what happens when I get -1. Oh, sorry. One negative sign changes everything. It's crazy. Okay, so I get, wow, I get okay. I get 1, -2, 1, 2, -1. And I get a whole bunch of zeros. Just make sure my matrix A is fine. 1, -2, -2. Wait, sorry. Also, no, it's fine. Then 2, 4, 3, -6, 3, 6, 1, -3. Yeah, this looks right. Okay. What does this mean? I have one pivot, right? And then what does this mean? I got 3 free variables. So then, according to this system, x1 is equal to what? 2x2 minus 3x3 minus, sorry, not 3x3. It's x3 minus 2x4 minus 1. So that's what I get from this first row of the row reduced echelon form. And what is x2 going to be? What is x3? What is x4? RST, which equals what? -1 plus 2r minus s minus 2t. So then what is the solution going to look like? x1, x2, x3, x4. This will be what? -1 plus 2r minus s minus 2t. I get r, s, and t. Then if I separate this out, I'm going to get -1, 0, 0, 0. I will get r, 2, 1, 0, 0. I will get s, -1, 0, 1, 0. And I'll get t. T is what? -2, 0, 0, 1. You guys see that? This is the general solution to the non-homogeneous system. Now, what is this? This is called the particular solution. Remember, R, S, and T can be any scalar. So if you plug in 0 to all of this, this solution will remain. And what I mean by this solution is that this solution solves the system. This one solution. If I make x1 being -1 and everything else being 0, that one solution works. But what else works? This is called the solution to the homogeneous system. Homogeneous. Why is this the solution to the homogeneous system? Well, I would get this row-reduced echelon form regardless, whatever this is. This solves the homogeneous system. So these bases, these vectors form a basis for the null space. So this always solves the homogeneous system, no matter what. So when I apply these vectors, right? Any combination of these vectors. So like think about this. So if this is A, right? And I do A multiplied by -1,0,0,0 plus any combination of R, S, and T. So like I'm gonna call this, okay, let's call this like let's call this particular solution XP and call this particular solution the general solution, call it XG for general. Actually XH for homogeneous. So if I do AXP plus XH, this equals AXP plus AXH. But since this solves the homogeneous system, I know this will be always 0, no matter what. And this will give me the particular solution here, the result, which will give me -1, -2, 1, 3. So this guy here always gets mapped to 0 when you multiply by that matrix A. This portion of my general solution always gets mapped to 0 because that represents the solution to the homogeneous system. And I just realized that the solution is also wrong, so I have to update that as well.
So if I can ask a quick question, so the particular solution would be the general non-homogeneous solution, and then whereas over on the other side is the homogeneous system solution?
Okay, so it's a good question. Again, what are we looking for? We're looking for the vector form of the general solution of the homogeneous system. Okay, so this whole thing is the general solution to the non-homogeneous system. This whole thing. A piece of it, though, is called the particular solution to the non-homogeneous system. So let me write that, be more explicit. So this is called the particular solution to the non-homogeneous system. And just for now, I'm gonna call it X sub P. Okay. Now you can try this yourself. Like plug in this solution into my system. You're gonna get the output, desired output. If you plug this in -1,0,0,0 and you left multiply to this, you're gonna get this. What does that mean? It's a solution. It's a particular one. Now, here comes the interesting part of this though. This is not the only solution. There's infinitely many. Now, how does the rest of the solution look like? Well, it looks like taking the particular one and then adding a linear combination of these vectors. And take any one you want. Make R, S, and T any numbers you desire. There's uncountably infinite possibilities. As long as you're adding a linear combination of these particular vectors, no matter what you plug in, right? No matter what you plug in for R, S, and T, and you add these all these vectors up, and you plug it in here, it will always give you it will always satisfy the equation. Now, these guys themselves, take away this away, just themselves, this is the general solution to the homogeneous system. Now, where do we get this stuff from? Well, we got it from the row reduced echelon form. If you made this a zero, right, and you perform the row reduced echelon form, like if you just made all these zeros and just perform row reduced echelon form on the matrix, and we've done so, you still get this matrix no matter what. You still will get these guys for x1, right? No matter what. So what you're getting in the procedure of finding the general solution to the non-homogeneous system, in my pursuit of that, automatically I get the solution to the homogeneous system. And that's the impressive part, that no matter what happens with this, no matter what any linear combination of these three vectors, and I add it to the particular solution, no matter what, this will always satisfy the equation. And these vectors under the multiplication of A, right? They always get mapped to zero by the very nature of what they are. They are the solution to the homogeneous system. So you're essentially finding two things at once. In finding the general solution to the homogeneous system, if done correctly, and you go through all the steps, you get a particular solution to the non-homogeneous system, and then you get the general solution to the homogeneous system, which when you connect these two things together, you get the general solution to the non-homogeneous system. You see how much more interesting this is than when things work out in terms of having a invertible matrix. In invertible matrix, you don't have this other things to worry about. I don't have free variables to worry about. I only have one solution for every single case. You understand? But when the matrix is not invertible, when your system is not invertible, then there's more possibilities to it. In this case, there's infinitely many. Does that make sense? Good. Any other questions?
If you have time for one more,
Well, that's why I'm asking.
um, the basis vector 3.1, I mean the basics for subspace, 3.1 question 2, part do part B.
This one? Is this the one?
Yes. Mm-hmm.
So we want to determine whether the following sets are subspaces. The set of all n by n matrices A such that the determinant of A is 0. Now, what does it mean to be a subspace?
has to satisfy all three of the
Conditions, right?
properties.
So
Yeah.
what are the three conditions?
It has to meet the addition
Closed under addition.
and by multiplication of a scalar,
Closed under scalar multiplication, and it must contain
and
the zero
that
vector.
one.
The zero
Oh,
vector.
okay.
That's the first one. Now in this case, our vectors are matrices. They're n by n matrices, right? That's what we're dealing with, n by n matrices. So our zero vector would be the zero matrix. So that's the first thing you should worry about. So is the zero matrix, so in this case, how would we write that? Some people write it this way. So the zero matrix is the n by n matrix, right? That has zeros in all the rows and all the columns. What's the determinant of such a matrix? What's the determinant of a zero matrix? Well, isn't it zero?
0.
Right? So is the zero matrix in this set that has a determinant equal to 0? Yes. It satisfies that first property of being a subspace, right? That's the first one. The third one, what's the third one?
Scalar multiply.
Scalar multiple, right? So if I already have a matrix in the set whose determinant is 0, and then C is some scalar. So what happens when I take the determinant of C of A? Well, according to the property, right? Don't I get C to the n times the determinant of A? But the determinant of A is 0. So guess what? This set is also closed under. It's closed under
Scalar multiplication.
scalar multiplication. So this set, the set is closed under scalar multiplication. So you notice I skipped number 2. Why did I skip it? Well, I wanted to show you the things that work. And then you can kind of already start to understand that it's not a subspace.
Mm.
Because why?
It's not closed under addition.
It's not closed under addition. Now how can I show that? So what that means is, let me bring this all together. Actually, yeah, I'm just gonna write it. I'm gonna bring this over here. Should have done this before. So this matrix, this set of matrices has a 0 matrix in it. This set of matrices with determinant equal to 0 is closed under scalar multiplication. Now, what happens if I have two matrices in this space, where determinant of A equals 0 and determinant of B also equals 0? Is determinant of A plus B also equal to 0? That's the question. Can you guys, so I'm already telling you this doesn't work, right? Now, can you guys give me a reason why? This is the hard part. So whenever you prove something to be true, right? You prove it normally in general, in a general way. Whenever you want to disprove something, all you need is one counterexample, and you're able to effectively say this is not true. So what you have to do is think about what scenario could this be where you have two matrices that are have a determinant that are zero, that are each zero, but when you add them up, the determinant is no longer zero. Can you guys think of can you think of two matrices that are have a determinant equal to zero, and when you add them up, no longer have a determinant equal to zero?
Uh, if A has two identical rows
Okay.
and B has one zeros row,
Yeah.
if we add them together, um,
Yeah.
um,
If you add
then
them together, then what?
then
Okay, so look. I'm gonna do this to you. So let A, right, have two identical rows, right?
mm,
Okay. A has two identical rows. And let B be the zero matrix. Then what is A
I
plus B gonna give me?
not I meant it's not zero matrix. It's like one rows zero.
Okay, so the reason why I'm mentioning this is because this is an example where this is true.
Oh yeah.
This will be true, right? This is here, and then this is here. We know the determinant of a matrix with identical rows, two identical rows is zero. If you add them again, it's still going to be zero. So then you
Mm-hmm.
would say, oh no, so this is true. And then you're giving me one where it has two identical rows, and you're saying one row of zeros. Now the question is, how do you know that when you add them up, you will get a non-zero determinant? Do you see, like, I believe you. I think you will have a matrix when you add those two matrices together.
Mm.
You will most likely have a matrix that is non-zero determinant. But how can you guarantee that for me? You understand? Like I believe you because I believe the scenario. But believability when you're proving something mathematically is not enough to prove it mathematically. How believable something is, right? Is something more subjective. Like, yeah, I think that can be true. But here is no I think. It's either yes, like I can show you this is true, or I say, no, look, there's a particular example of why this is false. Now, the thing you propose, does it always produce a determinant that's non-zero?
Mm.
That's where like I have to think, and I feel like I can come up with something where your scenario doesn't give what we desire, which is to show that this is not true. Like I feel like there might be a scenario where you have two identical rows. You're adding by a matrix with 1, 0 row, and you still will have a determinant being 0. I
Mm.
think that can happen. So that's the only thing I would say. That's not like it's not a definitive counterexample
Mm.
because you haven't proven to me either direction that this will always be the case. Even simpler. There's a simpler example, counterexample. There's a simpler one. Okay, so I'll just give it to you guys. All right. So like let A be this 1 0 0 0 1 0 0 0 0. Isn't the determinant of A 0? And then let B be 0 0 0 0 0 0 0 0 1. Isn't the determinant of B 0? Now what's A plus B? What's the determinant of A plus B? 1. And then you can generalize this idea to n by n. Take the identity matrix and just separate them into two matrices. You're going to have a row, at least one row, right, full of zeros. So you're going to have determinants of those that sum of matrices. They're each 0. But when you add them up, you have the identity. And the determinant of that is non-zero. So this is a counterexample to this. So what that means is this set is not closed under addition. Meaning that if I get two things in this set and I add them up, I will not get a resulting matrix of also a determinant equal to 0. So this is not a subspace. All right. Okay, guys, so I went a little over, try to make up for what we lost in the technical difficulties. So I'll stop the recording here.